Hey folks, Ms. Gosling here. In this video, you're going to learn about circular motion. By the end of the video, you'll be able to translate between circular and linear motion. So let's go ahead and start with a couple of definitions. So first of all, I just want to mention below we have one example of circular motion. It's a car driving around a circular track. We can also, of course, have circular motion occur on the ground. So for example, if you are driving on a highway exit like so, you are probably driving on at least part of a circular path. So let's go ahead and talk about some definitions then, because our displacement and speed are a little bit different in circular motion. So with circular motion, we talk about angular displacement, which we use theta to describe, or to represent. And we're going to measure that in radians. So what we will do is we will decide at some point is our 0 theta. And then if we pause the car at some point here, we can actually measure its angular displacement theta in radians, which is going to be the angle it is away from my 0 point. Now, I do want to mention we do measure this in radians simply because that makes our later conversions much easier. So the next thing I want to discuss is angular speed, which we use the letter omega to represent. You could see your omega right here. So angular speed is exactly what you would expect it to be. It's your angular displacement divided by time. So we've got angular displacement over time. Now you'll notice I mentioned angular speed, not angular velocity, and that's because we are measuring how fast we're going, but we're not measuring our direction in this class. We're only going to worry about our speed, not our velocity, when we're looking at circular motion. Now, if you may ask, well, how do I represent speed in circular motion, or velocity in circular motion? How do I represent direction? Because I'm not going in one constant direction. So usually with circular motion, we would represent our direction as our either clockwise or counterclockwise. But again, we're not going to worry about that for this class. So let's go ahead and move on and talk about a couple of problems. So moving on to two more definitions. We have period and frequency. And period and frequency are kind of opposites of one another. Two halves of the same whole, you could say even. So period is the time taken for one full revolution, which we measure in seconds. And frequency is the amount of revolutions per second. So period is time per revolution, and frequency is revolutions per unit time. So when I say one full revolution, I mean if I am on some circular path, so if I'm on some circular path like this guy, and I start here, my period is going to be the time it takes me to continue going around the circle and end up right back where I started. And my frequency is the number of times I can do that in 1 second. So we're going to give our period T. And I like to remember that period is a capital T because it's time, which is normally a lowercase t, as you know. But it's a specific kind of time. So it's time with a little more definition, kind of like the proper noun version of time, hence it's a capital T. And my period is going to equal 2 pi divided by my angular speed, which is going to equal 1 over my frequency. Now, with angular speed, I also want to look at the relationship between my angular speed, omega, and my linear speed, v. And here you're going to see a little bit of why we use radians. So you can see what the final equation is on top, but I do want to actually go through that derivation as well. So say that I'm going through some angular displacement theta in a given time t. What is my angular velocity? Well, I know that velocity is given by displacement over time, or really in this case, we're looking at our linear speed, so distance over time. And the distance that I'm going to travel is the length of this arc here. Now, you may or may not remember this from, I think, probably your geometry class. But arc length, or distance, is given by theta times r, if and only if theta is in radians. So my arc length is equal to my angle in radians times my radius r. So that means that I can write then that theta, since displacement is equal to theta r, theta is equal to my distance over my radius. Therefore, I can write then that omega is equal to theta over t, which is equal to d over r times 1 over t. Since we're replacing our theta with distance over radius. Flipping that around, I get that d over t is equal to 1 over r, because I can flip around the numerator of my fraction if they're getting multiplied together. Which means, now d over t, you remember, is velocity. So that means that omega is equal to linear speed divided by radius. And there you have it. That is our conversion. So now that we've done that, let's go ahead and go through an example. So a clock has a minute hand that is 8 centimeters long. Calculate the angular speed of the minute hand and the linear speed of its tip. So let's go ahead and start by drawing what's going on. So I'm going to go ahead and draw my circle up here. And I'll go ahead and draw my minute hand here. So I know that in 1 hour, or in 60 minutes, I'm going to go 2 pi radians. So it takes me 60 minutes or 1 hour to go 2 pi radians with my minute hand. I also know that the length of my minute hand is 8 centimeters. So let's go ahead and start by calculating the angular speed. And actually, we'll calculate them both together, because why not? So I know that my time t is 60 minutes, or 3,600 seconds. I also know that my radius r is 8 centimeters, or 0.08 meters, and you'll notice I am turning everything into my SI, my standard international units. And I know that my angular displacement theta is 2 pi radians. So from that, let's go ahead and calculate my two unknowns, omega and v. So I have two equations since I have two unknowns. And what I'm going to do is I'm going to go ahead and start by finding omega, because omega is equal to theta over t. And then I have a couple of options for how to find v, but I'm going to go the quick way, and I'm going to say v is equal to omega over r. So now that I have my equations written, I am ready to sub and solve. So I know that omega is equal to theta over t, or 2 pi over 3,600. Thus, omega is 0.001 radians per second. And I know that my linear velocity v is omega over r, or 0.001 radians per second divided by 0.08 meters. Thus, the linear speed of the tip of my